welcome to another episode of Interstigation. In today's episode of Interstigation, I will go over the sine limit. As you realize, this sine limit is actually not a derivative topic, but I feel like this is very necessary into derivatives because it helps with when we actually try to differentiate sine of x. And that's all of the basic rules that we need to differentiate polynomials, rational functions. That's all done. And from this point on, we're just going to differentiate special functions like exponential, logarithm, sine, trigonometric, or sorts of like that. As always, we'll start with the daily problem. The daily problem states that if we have, let's say, x squared over 7 plus y squared over 13 is equal to 1, and wants to find the rate of y changes with respect of x, which is find dy over dx. And pause the video if you want to take a try and proceed the video when you think you're ready. And this obviously is pretty annoying to deal with if you're actually trying to differentiate this explicitly. So actually, we're going to differentiate this implicitly as I taught from the previous video. So this one, x squared over 7, we need to take the derivative on both sides. So if we take the derivative on both sides, plus this, I actually used a sum rule over here so that it looks a little bit neater, and we actually skipped like one step, but it's actually not so necessary even when you're taking the AP test because it's very easy. And over here, over 7 is actually, you don't need to use the quotient rule because this is just, you can see this as 1/7 times x squared. So you can erase this and you can see that this is 1/7 times x squared. And you can erase this and say that this is 1/13 y squared. And this is just constant multiple rule. And we can take that out, and we want the derivative of that, that's 2x, and take that out, 1/13, and we want the derivative of y squared. Derivative of y squared, we actually need to use the chain rule over here. So that would be 2y times, using the chain rule, the thing that we actually want. I will color that in red. dy over dx, and the right hand side is just 0. And let's try to simplify that. That's 2/7 x plus 2/13y times the what we want. And dy over dx is equal to 0. Is equal to 0. And we can move this side to the other side, 2/7 x, and that's 2/13 y times what we want. And that would be equal to dy over dx, which is the derivative. And we can take this to the other side, divide that to the other side. So multiply by 13/2, 13/2y on both sides. And over here, you simply get, though the 2 and 2 cancel out, we just have negative 7/13 times y over x. Obviously, you can combine them into one fraction, but I would like to leave it like this. And this is our answer for this problem. Now let's take a look at the sine limit. The sine limit basically wants to find the limit value as x approaches 0 of sine x over x And we can take an intuitive feel about it using the sine graph, if you know about it. So the sine graph looks somewhat like this. Well, it just doesn't want me to draw a sine graph. It looks somewhat like this, and if x approaches 0, we want to find basically this, which is the y value, so y over x, which is basically we want to find the slope as this approaches 0. Basically, the slope, the derivative of it at a special point, and after that we can induct that to find the derivative value for every point on the sine graph. So if we take instantaneous slope over here, we can see that it is about 1. Maybe it will be some special values, but we will guess that it's just 1. Not greater than 1, it's just 1. It is equal to 1. And let's try to prove it. So proving it actually requires us using the unit circle. So if we have something like this, then if we have a sine value, let's say sine value over here, let's say that, and that this is actually 1, because this is a unit circle, and that we have this value as the absolute value of sine of x, because we know that this might go into other quadrants. Although if we want the limit as it approaches 0, we are only interested in quadrant 1 and quadrant 4. So this half of the plane. And we can color this area. So let's try to separate these areas so that we can use the squeeze theorem or the sandwich theorem or whatever you like to call it. So there are 2 boundaries. It is very hard to calculate like this curve or this line, but we can use 2 boundaries. One of the boundaries is the thing inside, which is just our x that we want, sine of x that we want, and one of the boundary is outside. So would we actually want to color this in different colors? Let's say the first color is green. Let's color this. Let's color this in over here. This triangle. Let's consider the area of this triangle. The area of this triangle would simply be 1, or the base, times the height over 2. So area green is equal to this, which is half of sine x, the absolute value of sine x. And the other portion, if we look at the arc, we can also find the area of this arc. So if we have this over here, let's say if we have this area, let's say it's purple, this area over here, then this area over here is actually an arc with the central angle, right? And the central angle is just simply x. And this is a unit square, so we can get that A purple is equal to this absolute value of x over 2. And if we have this third color, or the largest of them all, which is this area, the largest of them all, this area is also easy to prove because we constructed this as this is a right angle, and that we can use similar triangles to get this is actually the value of tangent x, absolute value of tangent x. And this area, this blue area, the sine area, so we can write that a sine is equal to the tangent of x over 2. And from the graph, we can see that this green area is less or equal to the purple area is less or equal to the blue area. So we can get that in a different color that sine x over 2 is less than equal to x over 2 is less than equal to tangent of x over 2. Obviously, we can multiply by 2 on both sides. We can multiply by 2 on both sides, like this. And let's say we have this. And this sine of x, we want this for that to approach 0. So let's see. Sine of 0, can we do this? Well, yeah. Because if we actually divide both sides or all three sides by sine of x, the absolute value of sine of x, this side would just go to 0. This side is absolute value of x over absolute value of sine of x is less or equal to this tangent of x. Although tangent of x, we can just write that as sine of x over cosine of x. We want that over sine of x. Well, that would just turn into 1 over cosine of x. And that we can take the reciprocal of this, all three sides of this, and notice that the sign will change. So that is 1, and that's sine of x over x. That is larger or equal to cosine of x. And we want the first and fourth quadrant only. So this portion only, and we know some basic range of it. Some basic range would simply be this x is from negative 2 pi to positive 2 pi, so first and fourth quadrant. And so this, we can just get rid of the absolute value sign, because we can just see that all of these wouldn't have a sign change, or they would have the same sign overall. Although the sine x might be negative, but when sine x is negative, x is also negative, so their quotient would just be positive and our sign don't need to change. And from now we can apply the limits, which we've said the limits would just simply be this. So we have this doesn't change, because we can take the limits of this, but it doesn't really matter because it doesn't include x. And this middle part is what we want, and the right part is the limit as x approaches 0 of cosine of x. And this is very easy because cosine of 0 is actually defined. So cosine of 0 is just 1, and this side is also 1. So this thing that we actually want to prove has to be 1. So the limit as x approaches 0 of sine x over x has to be 1 according to the sandwich theorem. Or if you look at this, there's no other values that this value can be. So this is our sine limit, which is a special point of the derivative of the sine, and we will do the sine derivative a few episodes later. Thank you for watching this episode of Investigation, and I will see you in the next one. Thank you.